all viruses, I don't care whether it's HIV or a virus that infects a plant, all viruses have two common things. One is they have a protein shell that surrounds on the inside a nucleic acid. What's a nucleic acid? RNA or DNA. So in a sense, all viruses are an M&M. And what we've done is take out the gooey chocolate in the middle and just leaving the shell. Take out the nucleic acid. So these shells now, these virus-like shells, can no longer be infectious. They're missing the machinery to be and the blueprint to cause a viral infection. But that shell is incredibly useful because now that's a container. So that same idea that viruses can be used for drug delivery can be extended to anything. It's really just a container, just like this teacup I'm holding right now. And so you can put a drug on the inside, but you can also put a catalytic material on the inside. And we know, and chemistry has taught us over the years, that metal clusters, in some ways like the metal clusters found in these hydrogenase enzymes, can be mimicked. And when you mimic them in a small confined area, like the inside of these protein cages, these viruses, you actually produce very high performance catalysts for making hydrogen. So you might ask, well, we've known how to make hydrogen and we're trying to switch to a hydrogen economy. What's the problem? Why aren't we there? And the real reason is some of the best catalysts we have are platinum. But we don't have enough platinum on this planet to produce the amount of hydrogen we really need to run a present-day society. So people are very interested in getting the same kind of catalytic efficiency out of these big clusters of platinum, but now out of a really, really small amount of platinum. And these viral cages that we pull out of places like Yellowstone allow us to do that. So it's pretty exciting, the work that's being done at MSU in advancing the efficiencies of these kinds of new catalysts for making hydrogen. It's something that any student at the university, and even down to a high school level now, are getting exposure about how do you actually do it. And it's a lot of fun. I mean, it's really a very enjoyable kind of experimentation that you go through to take a virus, genetically use the tricks of genetic engineering and chemistry to remove the nucleic acid on the inside, the gooey stuff, just leaving the protein shell. And then we actually have living factories that produce these shells for us. All we have to do is feed them essentially sugar, and they keep pumping out lots of these protein cages, which are relatively easy to purify, and then we use them for these biotech applications in medicine and energy.